Continuing on physical chemistry, chapter 15, we're in section 9 now. We're going to talk about the Boltzmann Distribution Law. So for an ideal gas, we have PV equals nRT. So solving for pressure, we get P is equal to nRT times 1 over V. Now we want to substitute that for out the moles for actual number of molecules. So we get pressure is equal to the number of molecules divided by Avogadro's number times RT times 1 over V. Now we want to use the barometric formula that we came up with in a previous section. So that's pressure is equal to P naught times E times the exponent minus mgz over RT. Remember, P naught was the pressure at height 0. Mass would be the weight of one atom, molecule. G, of course, is the acceleration due to gravity. Z is just the height above the arbitrary point, which we said the Earth's surface. R is the gas constant R, and then T, of course, is the absolute temperature in kelvins. So now we have the number of molecules at height Z divided by Avogadro's number times the gas constant R times the absolute temperature times 1 over the volume is equal to the number of molecules at height 0 divided by Avogadro's number times R times T times 1 over V times E to the molecular weight times GZ over RT. Now remember, NZ would be the number of molecules at altitude Z. So the RT, 1 over V, and NA on both of those sides cancel out. So at any height, we're going to have potential energy of these molecules. And if you change the height, you're going to have a change in potential energy of the molecule. So we're going to say the change in potential energy is going to be the potential energy at height Z minus the potential energy at height 0, which is going to be mgz. So we get the number of molecules at height Z is going to be equal to the number of molecules at height 0 times E to the delta, the change in potential energy, divided by kT. Now remember, we said in the previous section that we arbitrarily picked Earth's surface as the reference point. So at height 0, the change in potential energy is going to be equal to 0. Remember, potential energy is always compared to some arbitrary reference point. And in this case, we said Earth's surface will be easy enough. So we have mgz over RT is going to be equal to Avogadro's number times mass times gravitational acceleration times the height Z divided by Boltzmann's constant divided by Avogadro's number times the absolute temperature. And that's going to be equal to mgz over kT, and that's going to be equal to the change in the potential energy divided by kT. So we also have the number of molecules at height Z divided by the number of molecules at height 0, which is approximately equal to E to the power of minus change in potential energy divided by kT. So this is a special case of the Boltzmann Distribution Law. Now here's what the actual Boltzmann Distribution Law says. Let's say you have two energy levels, energy level 1, energy level 2. So you have a change in potential energy. So we're also going to have a certain number of atoms at energy level 1. We're going to have a certain number of atoms at energy level 2. So these represent two different potential energies. What Boltzmann's distribution law says, if energy level 2 is greater than energy level 1, then that means that the change in the Gibbs free energy is greater than 0, and therefore the number of molecules at energy level 2 will be less than the number of molecules at energy level 1. Now, so what we have is the number of molecules at energy level 2 divided by the number of molecules at energy level 1 is equal to the minus change in Gibbs free energy divided by kT. Now this is the Boltzmann distribution law, and this is useful for statistical mechanics. Now look at this graph I sort of squeezed in here. So we have two different energy levels here, energy level 1 and 2. They're kind of close together, so we have 4 and 4. We have about the same number of molecules in each case. But over here, we have energy level 1 and 2. Notice they're much farther apart. So we have 6 down here and only 2 up here. So what we're saying is that the larger the separation of energies, then you're going to have even less and less at the higher energy level. So for example, let's say at what temperature would the population of the state at higher energy level be? 1/10 of the state at the lower energy level. if the difference in energy is 1 kilojoule per mole. Well, then we just plug and chug. Here's n over 2 over n over 1, or number of molecules at energy level 2 divided by the number of molecules at energy level 1. That's equal to e to the minus change in energy divided by kT. So we have 0.1 is equal to e to the minus 10 to the third joules per mole times 1 mole divided by K, which is 6.02 times 10 to the negative 23rd per mole. And that 1.38 times 10 to the negative 23 joules per Kelvin times T. So we're going to solve for T here. It's a little bit of algebra, but the answer is 52.3 kelvins. So we have N2 over N1 is equal to e to the delta G over RT. That's e to the minus 5 times 10 to the negative 19 joules over 1.38 times 10 to the negative 23rd joules per Kelvin times 5,000 Kelvin. We get 7.13 times 10 to the negative 4. So N2 over N1 is roughly 1.4 times 10 to the third. So what this is saying is that at 5,000 Kelvin, you're going to have a ratio like 1,400 to 1 at did I get that upside down? Holy cow, I think I got that upside down. Yeah, no, this is flipped. That's why. This is flipped upside down. So yeah, you're going to have 1,400 times as many N1 than you do at N2. Okay, that's all for section 9.